In this video, we're going to cover Hess's law and how we can draw Hess cycles by connecting equations with known enthalpy changes. So this is why we need to be able to write equations for different enthalpy changes correctly from previous videos. We're going to use these cycles then that we've constructed to do some calculations of unknown enthalpy values of equations that are within these cycles. The way I teach this may be different to some of the teachers and from textbooks, as I want you to understand why the arrows point where they do in these cycles rather than just rote learn the method. So I find students that just rote learn the method find they get stuck on questions which are not straightforward. Hess's law states that the enthalpy change for a reaction is independent of the route taken. So that means it's not dependent on the route taken. And this is true if the starting and final conditions remain the same. So if the temperature and the pressure, etc., hasn't changed during the reaction. So we can illustrate this idea or understand this idea by looking at an enthalpy profile. So here's a cartoon-like enthalpy profile. We got an axis here to show energy. This is potential energy related to the height of the person, this child here. And at the start, he's a certain distance above the ground level. So he's got a certain amount of potential energy. So he's got 1.5 kilojoules potential energy. Now, if he jumps from that level to another level, his change in potential energy is half a kilojoule, 500 joules. Now, he could carry on jumping down and then jump back up again. But his overall energy change, because he started off up here and finally he's ended up here, is still 500 joules or half a kilojoule. So the overall change is still the same. So it doesn't matter that he's taken a longer route the second time round than the first time just by jumping from there to there or jumping from here all the way down to the bottom and then back up again. Since his starting position and final positions are the same, the overall energy change is the same. That's the idea of Hess's law, and we can look at this on a real enthalpy profile. So here's a real enthalpy profile for this reaction, which can be considered as NP formation of carbon monoxide because we're forming 1 mole of carbon monoxide, but I'm just going to call it NP change of reaction for this equation of carbon reacting with half mole of oxygen to give us 1 mole of carbon dioxide. So you can actually write this as F for formation. So we can't determine this value experimentally because there's no way you can burn carbon just to produce carbon monoxide molecules because some of the carbon will be converted to carbon dioxide. So practically this is impossible to do. But we can actually work this out by thinking about Hess's law. So we know we can have values of NP of combustion of carbon to give us carbon dioxide. If we burn the carbon in excess oxygen, we're going to make carbon dioxide. We can do this experimentally. So we know this value. So on the NP profile diagram, we can include that as this. So we're starting from carbon and oxygen. We're going to burn it to make carbon dioxide. I'm going to balance this by putting another half O2 on this arrow because the equation otherwise won't balance. So we know this enthalpy change to be minus 394 kilojoules per mole. We can also burn carbon monoxide to make carbon dioxide, so that can be done experimentally. We can start with carbon monoxide and burn it to make carbon dioxide, and that can be found. So we know that value, so converting carbon monoxide to carbon dioxide by burning it in air is going to be minus 283 kilojoules per mole. So Hess's law, before we do that, we're going to, let's balance the equation by putting half O2 on this arrow. Hess's law states that the enthalpy change for reactions, for this reaction, we want to know that enthalpy change. Hess's law says that this enthalpy change is independent of the route taken, so it's not dependent on the route. So as long as we start in the same place, end up in the same place here, it doesn't matter if I take this route from there to there, or if I take an alternative route, I can go from, these reactants here all the way around from there back to there. So we start at the same place and finish the same place. This enthalpy change is the same as this enthalpy change. So we can simply say that this value here, which we're going to call x, okay, that is going to be equal to minus 394, which is this value. So we go from this point down to this point. So we're going to have that point. So we have this value. Now this value here is minus 283. So going the other way is plus 283. So if I travel through an alternative route, let's say if I travel from here round to here, okay, so I start in this position here and end this position here through that green route, well, that is going to be minus 384, going from there to there is minus 384, and then we're going to go up this way, which is plus 283, because and this way is minus 283, going the other way is going to be plus 283, so this is going to be plus 283. And that gives us a value of minus 111 on the calculator. So you can see this visually on the diagram as well. So if I get rid of these, you can see that some of these two heights is the same as this height. So if I ignore the signs on these values, that minus that should give us that value, which is 111. And then we know this is exothermic because the arrow is pointing in the opposite direction to the axis. It's minus 111. So you can see this visually on an enthalpy profile. However, we don't tend to draw enthalpy profiles when we do calculation using Hess's law. We tend to draw what's called Hess cycles. I'm going to show you ways of drawing Hess cycles. So most teachers and most books will tell you two different ways of drawing Hess cycles, and you just learn them by rote. But I'm going to show you how we construct these cycles rather than just learning it by rote, because there are occasions where the information they give you, you just can't construct it just by rote. Okay, so for example, most teachers and most books will say that if you give NP combustion values and you want to work out the NP change for a reaction, let's say for this reaction here, that's what I want to work out the NP change for, and you give NP combustion of carbon, hydrogen, oxygen, and for this ethanol here, we draw the arrows pointing towards the bottom of this arrow, and you get the product's combustion here, and that's how you draw the cycle. And then if you give an NP formation values, you want to work out NP change for a reaction, you draw the elements down here and draw the arrows upwards. They don't tell you why, they just tell you to do that. Okay, that is fine for 90% of the time and it will work for most questions, but there are occasions where you're not just given NP combustion values and you're not just given NP formation values, you may be given a combination. I'll show you an example of that later. And then you're stuck because you just learned a method. You haven't really understood why the arrows point where they go. So this is why I spend the time to go over why the arrows go where they go, and we construct the cycle from scratch rather than just learn this method. Okay, so I'm going to do that with you next. So here's a question. We're given NP combustion values in a table, and we're going to work out the NP change of a reaction given these values. And we're going to construct a Hess cycle to do that. It just happens in this case that the NP change we want to work out for is an NP formation, and that's irrelevant. It doesn't matter what this NP change is, we can use the same method. It's irrelevant what this NP change is. It could be formation, it could be neutralization, it could be another combustion, it could be anything. So the first thing we're going to do is draw the equation for the reaction we want to work out the NP change for, which is this reaction here, and that's NP formation of propane. So that's what we're going to do first. So NP formation propane is forming 1 mole of propane from its elements. So we balance the equation for 1 mole of propane, and we can even put state symbols in. Propane is a gas. So that's the NP change we want to work out for. We don't know what this value is, so we don't know what this is. Okay, and we can put R here for reaction. In this case, we can even put we can even put F for formation, because this equation represents the NP formation of propane. But I'm just going to leave it as delta H. So the next thing we're going to do is we're going to write the equations for the enthalpy changes we're given, and then we can use those equations to construct an alternative route from the reactants to products. Rather than go from here to here directly, we're going to use an alternative route using equations that we're going to construct using these values. So the first equation we're going to write using these NP combustion values is the combustion of carbon. So by definition, enthalpy combustion of carbon is the burning of carbon in excess oxygen to give us the product of combustion, which is in this case carbon dioxide. So we know this value is minus 393.5, so I'm going to write that value on top of the arrow there. I do the same for enthalpy combustion of hydrogen, so that is burning 1 mole of hydrogen in excess oxygen to give us the product combustion, which is water, and we balance it for 1 mole of hydrogen here, and to do that we put half on the O2, and this value is minus 285.8. And we do the same for the propane, so burning 1 mole of propane in oxygen, we get carbon dioxide and water, and we balance for 1 mole of propane, so we put 3 in front of CO2 and we put a 4 in front of the H2O, and we balance the oxygens by putting a 5 in front of the O2. So this value is minus 2219.2. So what I'm going to try and do now is try to match the species within the equation we want to work out the enthalpy change for with species within these equations here that we've written. So first of all, I can see that the carbon here matches with the carbon here. So I'm going to pick up this equation at the top. I'm going to match the carbon with the carbon in the equation I want to work out the enthalpy change for. I'm going to do the same for the other equation, for the other elements. So I can see hydrogen here in the equation I want to work out the enthalpy change for. I can see that in these equations hydrogen appears here. So I'm going to connect those two hydrogens by picking up this equation and put it here. And I'm doing the same with the propane here. I can see propane is here, so I can even highlight it if I want to, match those, and I'm going to connect the propanes together and we get the propanes there. And all I'm going to do, I'm just going to tidy this up. So I'm just going to get rid of these bits of the equation on the left hand side or the reactant side. So I'm just going to delete those because we've already got these elements in the top here, so we don't really need this. Okay, so I'm going to just get rid of those. And then we're just going to move those arrows up. Now you notice then down here on the other side of these arrows, we've got the products of combustion for these species. So these are carbon dioxide and water. And what I'm going to do, I'm just going to group these together in a box. So I'm just going to tidy that up and put all these in a box together. So I'm just going to get rid of those. I'm just going to draw a box. So we could write carbon dioxide and water like that. We can leave it as that. Some people write products combustion in words down here. If you really want to be really thorough, you can even balance the equation. So with 3 lots of carbon, we're going to make 3 lots of carbon dioxide, and that should balance on the other side as well. So propane has 3 lots of carbon, and that should make 3 lots of carbon dioxide. So 4 lots of hydrogen should make 4 lots of H2O. And again, it balances on the other side, so the propane contains 8 hydrogens, which would make 4 lots of H2O. So we effectively created a cycle. Now, what I can do, I don't have to, but I can tidy this cycle up. I'm just going to draw the arrows slightly pointing to the centre there from the reactant side, going from top left to bottom right. And I'm going to push this arrow from the top right to bottom left, and we can see our cycle a bit clearer. You can see then there's my here's my alternative route going from this side around this way is my alternative route. So I could show that maybe drawing the alternative route in a different colour. So going from the reactant side to the product side through my alternative route via these 2 arrows on the left up towards against that arrow on the right there. So I've created my Hess cycle. So hopefully you can see that the cycle we produce represents enthalpy combustion of carbon to form carbon dioxide, and also enthalpy of combustion of hydrogen to make water, and enthalpy combustion of propane represented by this arrow to form water and carbon dioxide. So these arrow represents enthalpy combustion, and that's why they're pointing towards the products of combustion. So once we got this cycle, we can actually apply Hess's law, which states that the enthalpy change for a reaction is independent of the route taken. So we can take this alternative route, and that enthalpy change of the alternative route should be the same as the enthalpy change for the reaction. You can imagine that this is a bit like a map of a town, and you want to go from this side of town to this side of town through this path, but this road is blocked, this path is blocked. So you have to take an alternative path, and the rule is whenever you travel with the flow of the arrows or with the flow of the traffic, you keep the sign of the values. Here, where you're traveling against the flow of the arrow, we switch the sign of the value. So what we're going to do, we're going to work out enthalpy change for the reaction, delta H, which is this. So we're going to start from this side, we're going to travel with the flow of these arrows. So we're going to have minus 393.5. But because we got combustion of 3 moles of carbon to form 3 moles carbon dioxide, rather than just 1 mole of carbon to form 1 mole carbon dioxide, we need to multiply this value by 3. So this is going to be times by 3. We also need to include, because we're traveling from here to there, we're also going to include this arrow, because we're going with the flow of this arrow. We're going to keep the sign, so that's going to be plus minus 285.8 times 4, because we are burning 4 moles of hydrogen to give us 4 moles of water, and that will be 4 times the amount of energy released compared to 1 mole of hydrogen, which is 285.8. You could even write the multiplication signs on the arrows to show your workings clear if you want to. So we've gone partway through our journey from the reactant side towards this island. We're going to finish our journey here, and in the second part of our journey, we are travelling against the flow of the arrow. So if we travel against the flow of the arrow, we switch the sign of the value. So we're now going to have minus, so we're switching the sign, minus 2219.2. So because I'm going against the flow of the arrow, I'm switching the sign by putting a minus instead of a plus. So this time I don't have to multiply this value by any factor, because this is just 1 mole of propane undergoing combustion to the product's combustion there. So we've completed our workings out, and all we do is plug the numbers into our calculator to work out the enthalpy change of the reaction. So this is going to be 393.5 times 3, so that is minus 1180.5, and we're going to have, in this bit, we're going to have 285.8 times 4, so that is going to be, well, plus and minus is a minus, that'd be minus 1143.2. And then finally on this side here, we just have 2219.2, and a minus and a minus of minus is going to be a plus. So we're going to have plus 2219.2. So if we put the numbers into a calculator, minus 1180.5 minus 1143.2 plus 2219.2, our final answer is minus 104.5 kilojoules per mole. So we've worked out the enthalpy of formation of propane as this value. So here's another example where we're given enthalpy of combustion values for different substances, and we've got to work out an enthalpy change of a reaction. In this case, it happens to be an enthalpy of formation, but that's irrelevant. It doesn't really matter whether this is an enthalpy of formation, whether it's an enthalpy of neutralization, or any other reaction. The method is the same. We just need to draw the cycle to connect the left-hand side of the equation with the right-hand side for an alternative route. So I've written here the equations that represent the enthalpy of combustion of these substances, and we're going to connect the reactant side species with the product side using these arrows here. So I can see there's carbon in the equation I want to work out the enthalpy change for, and I can see within these sets of equations there's carbon here. So I'm going to connect those together. So I can see that I need to have hydrogen, and the only place I can see hydrogen is here. So I connect those hydrogens together. So I've sloped the arrows from the reactant side towards the centre already. So I can see there's ethanol here and there's ethanol here. I'm going to connect those together so I can highlight it in the same colour if I want to. So I'm going to connect those together. So I've sloped the arrow for the product side towards the centre from top right to bottom left, ready. So the only species in the equation I want to work out the enthalpy change for which hasn't got an arrow is the oxygen. Now that isn't a problem. I'll show you why that isn't a problem later, but I'm just going to tidy this cycle up. So I'm just going to get rid of the reactants on the equations here. Push the arrows up. I'm going to group these products of combustion into a box. I could write carbon dioxide and water here and not balance it. I can even write for OCR, they will accept products of combustion. I've connected two species on the left via an alternative route to the product on the right. The only problem is now I've got this oxygen which is not connected. I must connect all the species on the left to the species on the right. Now that's not a problem because I know what this value is, because if I try to burn oxygen or oxidize oxygen, that is not going to change oxygen. I can't oxidize oxygen, I can't burn oxygen. So the value of enthalpy combustion of oxygen is always going to be 0. So this value is 0. So now I've drawn my cycle and I've also put in the factors I need to multiply for these values, because I'm not just burning 1 mole of carbon to give us the product combustion. I'm burning 2 moles. I multiply this by 2 then. And here I need to multiply this value by 3 because there's 3 moles hydrogen burnt. And I could even put a half in front of the 0, but it makes no difference. That's going to be 0. I'm going to use Hess's law, which states that the enthalpy change of a reaction is independent of the route taken. So I'm going to take an alternative route, which is round this way. I'm going to draw that route in green. So I'm going to take that route in green. And again, every time I travel with the flow of the arrow, I keep the signs. When I travel against the flow of the arrow, which is here, I'm going to switch that sign. So I'm going to do my workings out. So delta H is going to be that, which is going to be, so plus minus 393.5 times 2. So it's plus because I'm going with the flow of the arrow. Okay, so with the flow of the arrows, that's plus minus 285.8 times 3. I'm going with the flow of the arrow, but this is irrelevant because adding a 0 times half is just 0. And I've reached halfway through my journey on this island. I'm going to finish my journey, and this time I'm traveling against the flow of the arrow. So I'm going to put minus, against the flow of the arrow. So minus 1367.3. And then put my numbers into a calculator. So plus and minus is a minus, and 393.5 times 2 is 787 on the calculator. Plus and minus is a minus, and 285.8 times 3 is 857.4 on the calculator. 0 times half is going to be 0, so plus 0. And a minus is a plus, so that's plus 1367.3. Putting all that into the calculator, I get minus 277.1 kilojoules per mole for the enthalpy change here, which is enthalpy of formation of ethanol. So we covered in this video so far how to work out the enthalpy change of a reaction using the enthalpy combustion values of the reactants and products for the reaction. And we do this by constructing the Hess cycles from scratch, and we can hopefully understand why the arrows point downwards towards the products of combustion. This video is getting a bit long, so what I'm going to do is do a second part where we can look at how we can work out the enthalpy change of a reaction using enthalpy formation values of the reactants and products. And again, we're going to construct the Hess cycles from scratch to understand why the arrows will point the other way. And by constructing these cycles from scratch, it will help you do questions which are not either of these scenarios. So you could get questions where you're not just given NP combustion only or NP formation only, or you can even be given NP values which are neither of these. So if you understand how to construct these cycles, then you will be able to do those questions. But if you just learn these two methods, which are shown in textbooks often, then you'll be stuck because all you've just done is learn the method without thinking about it.